So last class we were looking at square matrices that happen to have a pivot in every row. Okay. Now, so, so A is a square matrix, so same number of rows and columns, and okay. So when you do elimination, let's say you find a pivot in every single column. So you find n pivots in total. We said that every elimination step is reversible, and it corresponds to multiplication of a matrix on the left, right? So it's a multiplication of a matrix on the left because they are all row operations, okay? And why do we do row operations? We do row operations because we don't want to mess up the column relationships, and any column relationship is A multiplied by a vector on the right, okay? That equal A multiplied by a vector on the right equals 0 is any column relationship, okay? We neither want to introduce new column relationships nor do we want to destroy existing relationships. Okay, so in order to not mess up column relationships, we use reversible row operations, that is multiplication by matrices on the left that can be undone. Okay, you can sort of undo the operations. Okay, so you start with A and you do a series of operations on the series of row operations, all of which correspond to multiplying on the left by a matrix, right? So that means that if you take the net effect together, you'll have B times A will be an identity matrix, right? So, and it will be B times A will be an identity matrix because when you do all the row operations to reduce it to a row echelon form, there's a pivot in every column, right? So the the reduced row echelon form will be simply 1 0 0 0 1 0 0 0 1. So a matrix like this, and that we call it an identity matrix because multiplying this either on the left or right of any compatible matrix does not change the matrix. Okay. So any questions about all of this? So this is what we discussed last class. We also saw a bunch of things. We saw one of the things we saw was like it didn't matter how you did this elimination operation. So you don't have to use the standard procedure we use today. We did an alternate approach, and I wrote it as runs elimination, and like so run is your classmate. So it is not a special algorithm I was trying to teach you, just in case anybody had a doubt. It's not a special algorithm. It's like it is. It's no, we are not trying to learn that new algorithm. That's not what it is. The thing is, any reasonable way to do elimination. Okay, your individual row operations will all be different. Your intermediate matrices may all change, but as long as you have done reversible row operations, you can bring everything back. Okay, and when you do that, okay, if you look at the net effect of all your operations, even though you may have done something different, okay, the net effect of all your operations is going to be the same. It's going to be exactly the same. You multiply out all the matrices corresponding to your operation, you're going to get back the same matrix B that you would have got with standard elimination. Okay, this, and that is because we'll come to that. And this particular matrix that multiplies to the left of A and gives you an identity is going to be unique. Okay, so so any questions about how the row operations on A, which happens to have a pivot in every column, leads to this equation? So when you see this equation, this is what it means. Okay, any questions about any of this? So everyone is suddenly doing something else. Uh, so are there any, I mean, like, do you want me to go over any part of it, or should we step back and revisit any of this? Yeah. Okay, you tell me what the size of B should be. Okay, A is n by n. The identity matrix is the reduced row echelon form of A. Okay, and so what will be the size of this identity matrix? N by n. What should be the size of B then? Why? Why? Right, right. So the two outside ones, sorry, this is n by n, right? Okay. So this one, the second dimension has to match up with the first dimension. The numbers that are adjacent to each other should be the same, and this number has to be the same as this, right? So it forces it to be an n by n matrix. No, 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 that's not what I'm saying at all. I'm saying if A is a matrix like this, there exists B that satisfies this. Okay. Uh, so elimination gives us a matrix B. Right. So if A is a matrix that has a pivot in every row, in every column, then the elimination algorithm gives us the matrix B such that B times A is identity. Okay, that is very different from saying two multi. I mean, uh, is that clear? Is that clear? How we get this elimination how we get this matrix B? Okay, so why don't we? Uh, why don't we try this? Because one of the things I want you to do is to uh, one of the advantages of having these AI things is that they can give you a lot of examples. Okay, so it really helps to do a lot of examples. And you can have examples that suit you, right? So use the let's do one thing. Like, let's use the companion. Just pick a 3 by 3 matrix, a specific 3 by 3 matrix for A, and find me this B. Give me the elimination steps, and using the elimination steps, find B. So we are kind of repeating the uh, this one. I know there are some interface issues and everything, and we'll get to that. We'll get to that. It's like the pedagogy part is kind of more. We are focusing more on the teaching part rather than the interface part for now. So bear with us, like, when things are not perfect in the interface. Okay. Okay. So use your laptops. Use your laptops to go to this companion, and I want you to do this with me. Okay. So you may have to. Right. So you may have to log in. Uh, so go to the class web page. So does everyone know where the class web page is? Okay. Just log in. Okay. So my Zoom is kind of messing around. Uh, yeah. So use this to, okay, start with a matrix A. Okay. Start with any matrix, like a 3 by 3 matrix. Uh, ask it to do all the elimination steps and give you the matrices that correspond to each of the elimination steps, and ask it to multiply all of them in the right order to give the uh, matrix B such that B times A equals identity. I want you to give these instructions. Okay. Right. If you don't have a laptop on you, who doesn't have a laptop on them? Can you move with somebody else? Like Jeremy, do you have a laptop? Oh, but is it possible to type? You can type and everything? Yeah. Okay. Yeah. Okay. So, yeah, what asking it is so that's what I want you to figure out. Okay. I want you to, so there is this concept and we are trying to understand it, right? So, right. So give it a 3 by 3 matrix. Okay. Uh, when you specify 3 by 3 matrix, you can specify as lists of lists like in Python, or any other way it will understand. Okay. So it's not going to, no, just, no. So this is what I was saying. Like you probably need to refresh your, no, don't use the Lamaku one. Sorry, like I haven't updated the Lamaku. Okay. Sorry. I should update the Lamaco one too. I'll go from here. I updated on this, but not on Lamaco. Yeah. Okay, so give it a 3 by 3 matrix. Ask it to do elimination steps to bring it to the reduced row echelon form, and ask it to give the matrix that corresponds to every elimination step. Okay. Okay, so let me try. Let me see if Zoom will let me do this. Okay. Okay. Uh, so something like this. You can, matrices you can specify almost any natural way. It's not going to complain. Okay. It's oh, what is happening here? Is this a bug? Oh, it's not giving the answer. It's just uh, oh, is it happening to everybody? Okay, so maybe like there is some bug in the new deployment anyway. So use any other. So for this is a routine question. So uh, some of the questions, the answers that you'll get from regular AI bots, they're not really the greatest. That's the reason we have all of this. But for this is a very generic question. You can use like any other AI companion, I mean, any other AI bot. So use ChatGPT or anything else you want. Okay, which ones do most of you use? So yeah, on ChatGPT, just ask the same thing on ChatGPT. This is something weird here. Okay. Right. So generic questions like this won't hurt. But for more, but in general, like we'll fix this right away. But in general, like ChatGPT answers are the problem with ChatGPT and all these AI bots is they are their answers are meant to keep you engaged. They're not meant to tell you useful things. Okay, so the purpose is a little bit different. So some of the answers are not really useful for learning. So that is the reason to have this. But this is a very specific and generic question. It's okay. Um, I don't know if this is invertible. Let's do this first. You should be asking these things to give you a lot of examples. It can give you as many examples as you want. Like you can change around examples. You can do anything you do. I don't know why it's thinking so long, but uh, no, it happens because like the generic answers that are usually provided, they are usually so this what these language models do is they have memorized the internet. They have memorized every book illegally obtained. So as a result, like they are pretty good at they're pretty good at regurgitating patterns. But for you to get something useful, you need to force it to uh, look at information in specific orders. So right, so this is the first row operation. So it wants to eliminate the zero. Okay, and the way you would do it is row two. Uh, yeah. So sorry, this is the matrix A. Okay. Uh, so also notice. I for some reason you don't see some lines here, and I don't know why that is. Okay, so the way I gave the matrix is very so it's you can give it as lists of lists, but not even necessary. You can just write your numbers and put these. These are the LaTeX new line character, so it understands all of that. Okay, so anything you do that is reasonable, it's going to understand. You can use it by you can put a semicolon there or something. It will understand. Okay, now. Uh, this is the matrix. So what is the first operation we do? This is our first pivot, right? And because this is our first, oh, this one has turned out to be, I gave it a very easy matrix. It's already a lower triangular. Anyway, never mind. So, right. So what it should be doing is to get rid of this 2. Okay, and how does it do that? It has to be row 2 minus 2 row 1. Okay, so the row 2 is row 2, so it's using the standard elimination, so it's doing the same pattern that we are doing. Okay, row 2 minus 2 times row 1. Okay, um, and the operator that corresponds to that, it calls it the elementary matrix. It is this particular matrix. Okay, so when you do E times A, you get this matrix. Okay, now where is your second pivot? So there are no more entries below the first pivot that are non-zero. So what do? Move to the next column, next row, and your second pivot is this. Okay, you need to zero out entries below it. What operation would you do? R, yeah, R3 is R3 plus R2. Okay, and that is what it's doing. And so it looks at the second elimination matrix, uh, which is this, and then it obtains this matrix. Okay, and what you now need to do is to normalize. Okay, how do you normalize this one? The third row you need to multiply by -1. Okay, so the third row you need to multiply by -1. The operator there is first row leave unchanged, second row leave unchanged, uh, right? And the third row multiply by -1. Okay, and so that is it. Okay, so you would apply this. So essentially, E3, E2, E1, it's calling it A inverse, but that is the matrix. That is the matrix B that we want. Okay, you should ask it to give more examples. You need to do at least several minutes. It is really helpful to see many examples. Do as many examples as you can. Uh, Ideally, so like later today, when the AI companion is fixed, I'll let you know. So do these operate, I mean, find examples, ask it, force it to give you examples. Okay, it is pretty good at trying to understand what you want, even if you do not specify it fully. So that is actually a strength of all these language models, and that we retain in the companion too. Okay, so it is fairly good at trying to understand what you want to do. Okay, the companion is better because it doesn't ramble. It gives you more specific and more to the point answers, and it uses like class material. And more importantly, if it says something wrong and it is not uncommon. Okay, so it is not uncommon for these things to hallucinate and give you things that are completely off base. Okay, but if it does that, we can catch that. Okay, yeah. No, it just introduced a terminology we never used in class at all, and that's one of the reasons to not. That's one of the reasons we are using the companion and not this. The particular operators. These are all the row operations. These are all the matrices corresponding to row operations. They just have a name. They're called elementary matrices. Uh, then that elimination is the procedure where you do all these row operations and bring it to the reduced row echelon form. Every step corresponds to a specific row operation, and all these specific row operations, which are the simple row operations that we do, they're called elementary row operations, and the matrices corresponding to them are elementary matrices. Yeah, yeah. It gives you all of that because it's using like a very so this is fairly generic terminology. Okay, but is this clear? So force it to give you examples. Okay. Um, now, okay, so let's go back. Uh, right. We also saw that. Uh, so if you do a bunch of operations, and normally you would do first a series of uh, row operations to eliminate entries below pivots, and each of those operators uh, will be a lower triangular matrix. Okay, and then you will normalize all the pivots. That tends to be a diagonal matrix, and then you will do a series of operations that zero out entries above pivots, and they usually correspond. They not usually. They always correspond to upper triangular matrices. Yeah. That's right. Right. Right? So when you're zeroing out entries below pivots, you will be using operators that are lower triangular matrices also. Okay. And in addition, all these matrices except the diagonal matrix, except this matrix, all these matrices will have ones on the diagonal. Okay. Right. So this times A is identity. Okay. And when you reverse all the sequence of operations, okay, we saw last class that this means that A is uh, okay. We saw last class that you need to reverse from the outer end. Okay. So you have done this series of operations. When you want to undo all these operations, you undo the last operation first. Okay. Right. Remember, like you put on socks, then shoes, but when you want to remove them, you remove the shoes and then the socks. Okay. So the last operation gets undone first. So that is U3 minus. But then so I'll just do the first couple of steps just to remind ourselves. So when you undo the last operation, you have U2, U1, D, L3, L2, L1, because we have undone the last operation times A is U3. Okay, so you multiply by U3 inverse on both sides, okay, to undo the last operation. Then you would multiply by U2 inverse on the left by both sides. Okay, remember when you multiply by the same matrix, if you have any equality, if matrix multiplication is compatible, you're allowed to multiply by the same matrix on both sides. But you need to be careful. You can't, if you multiply one side of the equation on the left by a matrix, you need to multiply the other side of the equation also on the left by the same matrix. Okay. So here, if I'm going to multiply by U2 inverse on the left, I need to multiply on the left. Otherwise, U2 inverse does not see U2. Okay. If I multiply on the left by U2 inverse, I need to multiply on the left here as well. Okay. So that is why, and that is why you end up getting A to be equal to this. Okay. Wait, what is this? Right. Now, if A is equal to this, then it also follows that this matrix is B. Okay. All the elimination steps put together, that is equal to the matrix B. Okay. And we will have A times B to be also identity. Okay. Now, when we see this, so this, when we saw B times A equals identity, we are saying elimination brought A into the reduced row echelon form, which happens to be identity. Okay. That's what we read when we see that equation. Okay. Once again, like notice, like throughout this class, we hardly ever speak of individual matrices, individual numbers in a matrix. Okay. We almost never do that. We think in terms of columns of the matrix or rows of the matrix. And now when we see this matrix equation, we are saying, okay, elimination can bring A into the identity matrix. Okay. We are now talking of an algorithm. When I see this matrix equation, I'm not looking at it numerically at all. I'm saying elimination brings this matrix A into the identity matrix. Okay, that's what I see. Okay, the now because of this, like we think a little more and we realize that if elimination brought A into this identity matrix, then it will also happen that A times B is identity. Okay, why? Because B has to be equal to this matrix. Okay, if B is this B happens to be equal to this matrix, and from the elimination procedure, when you undo the elimination procedure, you will get that A equals this matrix. Okay, now when you multiply A and B together, what happens? When you multiply A and B together, uh, so A has a new representation. I mean, it was the matrix that was given to us, but we found, because of the elimination procedure, we found a different representation for the matrix as this long product. Okay, so A and B are these two matrices, this one. But if you look at this product, the associative law tells us we can multiply any two adjacent matrices together first. We can't mess up with the order of the matrices, but we are allowed to choose which matrices to multiply first. Okay, so obviously we would multiply these two. Okay, and that gives us the identity. Now the identity just, it's just like multiplying by 1, goes away. Then you have U2 inverse next to U2. Okay, so you multiply it, these things go away. Then U1 inverse U1, D, L3, L2, L1. Okay, so the whole thing cancels off and gives you just the identity matrix. Okay, and this is like amazing because it tells you that if elimination brought it to the reduced to the identity matrix, okay, then it also means that A times B is the identity matrix. A times that matrix is the identity matrix. But when I see A times B is identity matrix, what do I think? Right? So let B be, so B has n columns, and I'm going to write these columns as B1 through Bn. Okay, each of these B1 is a column. It's a column with n numbers. Each of this is a column with n numbers. Okay, I'm writing it like this because I don't want to keep writing so many rows all again and again, because I'm not thinking of individual elements. I'm thinking of each column. Okay, now B is all of this, and this equation tells me that A times B is identity. Okay, that means A times, okay, now in order to get the first column of the identity matrix, okay, I I know how do I get the first column of the product. So this I'm just going to write like this 0 1 0. Okay, how do I get the first column of the product? The first column of the product is a linear combination of the columns of A. And where are the coefficients? In B1, in the first column of B. Okay, so this actually means that A times B1. So a linear combination of the columns of A will give me this vector 1 0 0. It has zeros everywhere except one in the first position. Okay, now if I treat this as a equation, if I treat this as a system of linear equations, okay, so I'm asking solve for Ax equals this. Okay, now we know there is a solution, and that one solution is B1 because we just saw A times B1 is this 1 0 0 0 0. Okay, how many solutions are there? To ask how many solutions are there, what do you usually ask? It is, are there free columns in A? Are there free columns in A? No, because we started off by saying that A has a pivot in each column. A has no free columns. Okay, that means that Ax equals this has a unique solution. Okay, so it not only that B1 satisfies this equation, in fact, B1 is the only vector that satisfies this equation. Okay, so we could have got the first column of B instead of doing elimination. We could have got the first column of B by solving this equation. Okay, and in fact, we could have got the second column of B. Okay, how would I get the second column of B? How would I get the second column of this matrix, that is B2 here? In exactly the same fashion. Yeah, A times B2 will be what? What will be A times B2? Yeah, the second column of the product, which is 0 1 0 0 0 0. So okay, the when you have A times the second column here, you're going to get the second column of the product, and that is 0 1 0 0 0. Okay, now A times B2 is this, but it also follows that B2 is the only solution of this set of linear equations. Okay, Ax equals 0 1 0 0 0. The only solution for this set of linear equations is B2. Yeah. Oh, okay. So if A had a free column, what would have happened? The reduced row echelon form would not be this at all. Okay. So we would never get if A had any free column, okay, when we did elimination, when we did elimination, this would not be the matrix at the end at all. We would never have an identity matrix here. So it kind of breaks down right away here. Okay. So if A had a free column, you actually would not find a matrix B such that B times A is identity. Okay. Now that said, like in a different context, uh, suppose uh, without this context at all. Okay. So in isolation, I give you a matrix A times X equals 0 1 0 0 0, and let us say there is a solution and A had free columns, then there would be infinitely many solutions. Okay, but if I give you a matrix A, x equals 0, 1, 0, 0, 0, and if A has free columns, okay, then there is a possibility that there are no solutions either. Okay, if A is square and it has free columns, it's also possible that there are no solutions at all. Okay, so both the only thing that is not possible here is a unique solution, but both the other cases are possible. Either it has no solution or an infinite number of solutions. They're both possible. Yeah, right. But in this case, where where A has pivots in each column, okay, the second column of your net elimination matrix is also the unique solution of this equation. Okay, so it's a completely different way to connect elimination and solving equations. Okay, and it applies only for square matrices, but nevertheless, it's very interesting. Okay, does this make sense? Right, so we could actually get the columns of B instead of doing elimination. We could get the columns of B by solving a bunch of linear equations. Right, and in fact, that is the common. We no longer have to do any of these things by hand. But long ago, when people tried to hand compute these things, this used to be the way they computed. This used to be one way to compute inverses. Okay, so you would start with a matrix A. Okay, and you would augment it in order to solve equations. You augment the target. You take this matrix A, you take the target, you look at the augmented matrices and do elimination, right? So that's what they do, except instead of solving for each of them separately. Okay, so what happens here is, like, if you take A and this vector and you do elimination. When you're doing elimination, the first n columns of A will give you n pivots. After that, there are no more pivots. Okay, because you'll have found a pivot in every row at that point. And so till then, all the elimination steps, okay, they only depend upon A. They don't depend upon the target. Okay, because you haven't come till the target column, right? So the operations you're going to choose will only depend upon A. And beyond that point too, when you zero out entries above the pivot, okay, same story. Because all the pivots are in A, the operations you're going to choose are purely determined by A. Okay, so when you're solving for different targets, it's not as if you're going to do different operations. The operations you do are going to be the same always. So might as well put all the targets together. Okay, so what you do is you do elimination. You do elimination on this matrix. So you take A, this has 2n columns, n rows and 2n columns, because this has n rows and A itself has n columns, and the identity matrix has n more columns. So totally 2n columns, right? When you do elimination, all the steps of elimination are completely determined by A. Okay, so you keep getting to the reduced row echelon form. When you do all the way till the reduced row echelon form, the first 10 columns are going to be pivots. The others are going to be free columns. But by the time you get to this, but when you get to this, when you get to finding the pivots, zeroing entries below the pivots, normalizing the pivots, zeroing out entries above the pivots, you get the identity matrix here. But what you get here is the solutions for all of this. So that's your matrix B. Okay, so you'll get B automatically here. Okay, and we saw this matrix, we have been calling it B, but actually it has a name. this matrix is called the inverse of A. It is unique. There's only one inverse for A, for any matrix A, which has a full set of pivots. Okay. Now, the notation that we use uh, for B is A inverse. Okay, it's the undo operation for A. Okay, we know how to undo elementary row operations, but a large matrix A, which is not one of these elementary matrices, also does an operation on other matrices. And if A is square and it has a pivot in every column, its operation can be undone. Okay, and the operation that sort of undoes the operation of A is A inverse. Okay, so we'll stop here. I mean, this is like a very minor rendering bug, I think. So by afternoon, we'll fix this, but uh, generate lot of examples. Okay, so I'll give this to you as an assignment as well. For all these concepts, I want you to use the AI to generate examples. Okay. Okay, so I'll see you Monday. Okay. Thank you. Yeah.